Today we're going to cover the current state of landfill methane estimation, measurement, and monitoring. This is a field where there's been methods been used for many years and continue to be used, but their accuracy is questionable. And there's methods that are being developed and new technology that's being used that we're trying to see if those can improve the way we look at methane and the way we evaluate methane emissions from landfills. Landfill emissions estimation been primarily done in a couple different ways. And the most common way has been either modeling or estimation of those emissions, which does not rely on direct measurements and really only uses a certain amount of site-specific data. The first area that we look at is landfills that don't have gas collection. So really all we have are surface emissions coming through the landfill cover. There really is no measured data there to use. So with the models, we essentially have to rely on simply using our model estimations of the amount of methane that's being generated by the landfill and assume a certain amount of that is being emitted. The most common model for that is our first order decay model. That's been used for many, many years. There's various versions of that model, including international models. The main model that developed by the U.S. Environmental Protection Agency, which is called the Landfill Gas Emissions Model, or LANGEM, which is probably the most common. And the state of California actually has its own version. It's a bit of a hybrid of the international model. They're all really based on some early work done in the 1970s in a Shoal Canyon landfill in Southern California. So what's the basics for a first order decay model? It takes an amount of the waste that can actually degrade and produce methane, which can either call the L sub naught value or the degradable organic carbon value input to the model. Also, there's a K value, which is the decay rate, how quickly the waste breaks down to produce methane, and that, of course, is rainfall dependent, since it's dependent on the amount of moisture in the landfill. And then finally, of course, you input the waste tonnages, usually on an annual basis, and then you can estimate the amount of methane that's being generated. EPA's model really just looks at all municipal solid waste together, whereas the international model allows you to break the waste stream up to its component parts, and it probably provides a little more accurate estimation of the likelihood and the amount that the different waste components would generate in terms of methane. So what are the strengths and the weaknesses of the first order decay model? Really, the strength is that you can use it at any site as long as you have waste data. It's very low cost and pretty easy to use, and there are ways to refine it using the the international model, for example, when you look at actual waste characterization data, if you have that. What are the weaknesses? Well, like any models, there's a lot of uncertainty, a lot of inaccuracy with these models, and when you're using them for emissions estimation, you expect that there's a range of error in those numbers. No way to validate them, particularly on landfills that don't have a gas collection system, because you have then no measured value to use. And really, there's very limited options other than waste characterization data for site-specific information. So all in all, they're generally inaccurate and uncertain, but sometimes they're the only tool we have. There are some non-first order decay models that have been developed in terms of alternative ways to estimate methane emissions by model. None of these are really captured or designated in any regulatory framework, so they're really only used for research purposes. There's a model developed in California called the CalMIM model, developed on a contract with the California Energy Commission and state air agencies, and it allows you to model methane transport through the landfill surface. Soil moisture is a big component of that. So it represents one of those models, but it's not in very common use and not a lot of site examples to use to draw from. If you do have a gas collection system, that does provide a little bit of extra data. Now you have the actual amount of gas that's been recovered, so that's a measured value, and you can use that to calibrate or judge how well the model is predicting the emissions. Sites with gas systems can either use the amount of methane that's being generated via the model and then compare that to the amount of gas that's being collected and assume that the residual amount is the amount that's available for emissions. So that does mean you have to rely on the first order decay model, and that, we already talked about the error that introduces. Although the uncollected methane could be emitted, we know not all of it is, because regardless of whether they have a gas system or not, there is a portion of the methane that is oxidized in the landfill cover, and so that factor is applied to that uncollected or fugitive amount of methane to ultimately estimate what we consider to be the emissions of methane from a landfill. The strength of us using the first order decay model on a site with a gas system is that at least you have some data to validate the model, and then you can use that for calibration. And most sites that have gas systems really should have the kind of data we need in terms of the flow and methane content of the gas that's being collected over time. Obviously, it has the same weaknesses involved with the model and the inaccuracies and uncertainty. And this is sometimes where we find just how uncertain and how inaccurate some of these models are, because there have been cases where we have looked at the actual recovery data and discovered that we're actually collecting more gas than the model suggested would even be generated in the first place, or alternately the amount of recovered gas is a small fraction of the generated amount, and we know that's not accurate, because if it were, we would have major emission and odor issues, and we're simply not having that. So there is a built-in check that you get with the actual recovery data in terms of how accurate your model may be. There is a way to also estimate methane emissions without using the model. And in this case, we make an estimate of the collection efficiency of the gas system, and you combine that with the actual amount of gas recovery and use that to predict the residual amount of gas emissions. Those collection efficiency values can be obtained from default values from regulatory agencies, or they can be estimated in the landfill industry via the Solid Waste Industry for Climate Solutions Group actually developed a methodology for estimating the collection efficiency of a landfill based on different cover types and other parameters. That methodology was actually adapted into the US EPA Greenhouse Gas Reporting Program. And as with all of the methods, methane oxidation is of course applied at the end to any residual gas that's not being collected. So what are the strengths of that? You don't have the model, so you don't have some of the unrealistic or uncertain values that you get from using a model. And again, anytime you have cover information or gas recovery information, which really should be any landfill with a gas system, you can use the model. The weaknesses are that if you use a fixed collection efficiency, a default value, regardless of what you do in terms of the gas system and how much you improve it, you always end up with the same collection efficiency, and therefore as you collect more gas, your emissions actually go up, which of course is counterintuitive. So the methodologies are also biased towards different cover types and areas, which don't always tell the full story. The methodology that EPA adopted into their greenhouse gas program actually only uses average values for the different type collection efficiencies for the different cover types, so that really fixes your values. The full SWIX methodology allows you to a range of values based on how well the gas system is actually performing, including surface monitoring and other monitoring data. You can use the CalMIM model to estimate residual emissions after a gas collection system. It does have a module where you can apply gas collection, and but it does not use the recovered value to simply assigns different collection efficiencies for the gas system. So that has its pros and cons as well, but it is an alternative to using a first order decay model or using the cover-based collection efficiency model. So let's move on to landfill methane measurement. So this is cases where we're trying to actually measure the rate of emissions from a landfill using different techniques. This is much more expensive than the different estimating techniques that we just went over. It could be as much, 10 times more, as much as 100 times more, depending on the different methodologies. So while it may cost you several thousands of dollars to do a model and an estimation, it could cost you hundreds of thousands of dollars to do one of these more elaborate methane measurement techniques. We do think it can increase the accuracy and give you some real site-specific data, but the models, the methodology really are still in development. There's no definitive version of most of these methods. Some that people were promoting several years ago, including things that EPA were promoting, are no longer being recommended. And all of them have some form of algorithm or black box, if you will, where you take some of the measured data and use it to calculate a rate of emissions or a flux of emissions that's actually going through the cover of the landfill. One of the first methods is the flux chamber testing, and it's a way to measure the amount of going through the surface of the landfill. Typically, we have flux chambers that are up to a square meter. Most of them are smaller, and they're laid on the surface of the landfill, and then you measure the amount of gas coming into the flux, into the chamber, and then you extrapolate that of the landfill. Obviously, since you're only able to measure a very small area, there is some error in extrapolating to a very large area like a landfill, which can be hundreds of acres. EPA developed this methodology for use in site remediation, and it's been applied to landfills. If you follow EPA's model directly, you could, even a very small landfills could end up collecting numerous flux chamber samples. And of course, the more chambers, the more analyses, the more expensive it gets. There have been some alternatives where they've used surface emissions monitoring as kind of a screening tool to determine the different areas of the landfill, and particularly to identify any hotspots that you want to make sure you don't miss, and then reducing the total number of chamber locations using the pre-screening data. Again, even though this method has been used and has been used in some regulatory and non-regulatory environments, it doesn't have any formal regulatory approval for its use on landfills. There are also plume measurement techniques, and these are optical techniques where lasers or infrared devices or beams are shot across the surface of the landfill, and then there's reflectors and other things that measure the diffraction of those beams as methane passes through them, and they use that to measure the rate of methane emissions. There was a methodology developed by EPA and it included that, although right now EPA themselves are not even recommending that methodology due to some of the issues they had when they did some research studies themselves, including the repeatability of the results, weather conditions that would affect it, site configuration, the large size of the landfills, the topography of the landfills, and even the wind conditions. Other methodologies are termed micrometeorology, and basically you're still using similar optical sensors, but these are placed at different heights above the surface of the landfill, and those are co-located with meteorological measurements, and multiple readings are taken over time at these different elevations above the surface, and ultimately used to develop a flux rate for the actual methane passing through the cover. Eddy covariance is a common one of those and has been used at different landfills. But again, Don't have a lot of field use, particularly on landfills. There's no regulatory method that's been approved for it. Of course, they still use those back-end algorithms to calculate emissions, and that produces some degree of uncertainty. There are commercial packages for these, but they are expensive. The equipment itself is expensive, as well as any test study. There are several research projects that are ongoing at landfills, and we maybe will see some of that data in the near future. Reverse air dispersion modeling is a technique that's been used on various sites around the country, and basically it uses a typical air dispersion model but does it in reverse. So it takes the measured methane concentrations that we derive from like a surface emissions monitoring event, and we use the model in reverse to calculate what emission rate we would need to have to result in the measured concentrations of methane that we're seeing above the surface of the landfill. But like any model, it's a model and has those the uncertainty that goes along with any sort of model. One area of uncertainty that we have discovered in using this methodology is that it's very sensitive to hotspot areas. So if you have an area on the landfill that is tests for very high levels of surface emissions, we believe that this methodology can over-predict the rate of emissions that you would have to generate those surface concentrations. So not sure if this method is suitable for all landfills. It has been used on some landfills that have very low emissions and extremely good surface emissions monitoring data, and has predicted some very low rates of methane emission. So to sum up the measurement methodologies, and these are expensive, maybe in the high tens of thousands of dollars to even the low hundreds of thousands to even multiple hundreds of thousands, depending on the nature of the study. Many of them are one-time events, though the micrometeorology certainly can be set up for long-term events. They generally provide a snapshot in emissions, so you have the issue of trying to show that is representative of emissions throughout a year or over some period of time. And flux chambers probably have the most use on landfills and most data, but again, they're expensive and they have their own pros and cons in terms of what the accuracy might be. We do believe that the micrometeorology is probably the most emerging method right now, and that's certainly the one that the EPA's research department is recommending for landfills that are going down that research route. So the third component is landfill methane monitoring. So these are techniques that don't necessarily try to estimate or measure the emissions, but rather just measure the concentration of methane above the surface of the landfill as a means to determine where emissions might be occurring, where we might have hot spots. We're going to look at the traditional surface emissions monitoring methods that are built into the federal and state regulatory programs. We're going to look at both ground level and low altitude imaging, as well as satellite and aerial imaging. So surface monitoring, we've been using this for many years. It's a handheld device, detects methane above the surface of the landfill. There's an EPA method that is prescribed for this, EPA method 21. Typically we see flame ionization detectors, lasers, and several other devices that have been approved for use for this type of monitoring. When we do surface monitoring, there's several parameters that you'll deal with. The frequency of the monitoring, in most regulations that's quarterly. The monitoring path, in the federal statute, that's a 30-meter path, a serpentine path across the surface of the landfill. In California, that's actually a 25-foot path, so much tighter. Most of it is instantaneous monitoring, though California does require an integrated monitoring as well. Integrated means you actually take an average reading over a certain area, and that average reading is compared to a different threshold. The monitoring thresholds that are built into the regs are 500 parts per million by volume methane, and that's in the federal statute, as well as in California statute for instantaneous readings. The California regulations have a 25 ppm threshold for the integrated samples. And then whether you have to monitor penetrations through the cover above and beyond the serpentine path. Here's a quick summary of EPA versus California monitoring and the similarities that they have as well as their differences. most importantly, because of the tighter spacing and the additional integrated monitoring, the California program is significantly more expensive, 3 to 4 times more than the federal. So, in summary, surface monitoring certainly has a long-term use. The earliest we can date it back to is 1987 in the South Coast Air Quality Management District, which was the first jurisdiction to have a landfill gas air quality regulation. Then in EPA, we started the monitoring in 1998 under the federal New Source Performance Standard, and then California had its statewide rule, which is considered the most stringent in the U.S., and we've been monitoring in California since 2011. So a range of options and costs, and they're definitely scalable. There are some weather limitations that are built into the regulations, and those can be have to be dealt with. In some cases, you have to obtain alternatives to allow you to monitor in certain weather conditions in an area. So beyond the traditional surface monitoring, we do have some other options, and these involve the use again of imaging, optical imaging, infrared, laser, or other type of spectrum cameras that allow us to see methane emissions from a landfill and to actually measure the concentrations. Very common use of these types of techniques in the oil and gas industry for looking at pipe and equipment leaks. Not as much use in the landfill emission side of things, in part because landfill emissions tend to be a little more dispersed, so some techniques don't see them very well, and they don't because there's not enough contrast. But they have been used at certain landfills, and they have been successful in actually finding hotspot areas or leaks from landfills or landfill gas equipment, for example. So they have been used, and I think we're starting to see more and more use of these. The drone imaging is probably the biggest emerging area, and we're seeing more and more of this, and I think we will see more of this, and probably has the biggest future potential. Both the cost of drones themselves and the cameras have come down. There's more and more options for drones outfitted with the necessary cameras. They can increase the speed of the imaging and the surveys. They can get us to terrain that's not easy to traverse with human personnel walking the path, and they can repeat these monitoring events over periods of time. So I think we will see more and more use of drones in this capacity. The costs right now are still higher than just a what you might term a manual surface monitoring event, but I think they're getting cheaper. And now with drones more plentiful, I think we'll see more and more of that type of monitoring. Right now, they're not approved as an alternative in the different regulatory programs, but that is something that is being worked on, and it would take a research study to show that results can be repeatable and comparable to the traditional surface monitoring required in the regulation. High altitude imaging involves the same types of cameras, but we're talking about airplanes or satellites. Plumes have been detected and monitored in a very limited number of circumstances. These are definitely very much research type studies, and clearly very expensive because of what it involves. There was a major study of large landfills in the Los Angeles area. There was a study of a large natural gas leak also in the Southern California area. And then finally, NASA Jet Propulsion Labs actually did a study of landfills, compost facilities, wastewater plants, and oil and gas operations up and down California, and presented those results, demonstrating the use of the airplane-based imaging that they have. And certainly because they are NASA, some of that was some very sophisticated equipment. This is really too expensive for any type of regular monitoring at landfills, but certainly can be done for special occasions or research projects. We've also seen them used in litigation. Because of the altitude and the sophistication of the equipment, you may or may not be able to see low-level emissions from certain landfills that are small or well-controlled. But again, the NASA study was able to see methane plumes from a lot of landfills, and they actually were able to convert data into actual emission estimates using their own algorithms. So they not only took it from the imaging and concentration hotspot measuring, but they were actually able to turn it into emission rate or flux measurements. The California Resources Board is actually purchasing and going to deploy a satellite that'll be specific for methane measurements across the state of California as part of their greenhouse gas program. So we expect to see more and more of these types of imaging to occur, and whether they'll continue to evolve or whether they'll have other options for monitoring, and whether they can actually be used to calculate or estimate emissions remains to be seen. But right now the pricing remains probably too expensive for any sort of reasonable site-specific deployment, but we'll probably see them continue to be used as a research tool by regulatory agencies and other scientific bodies.